You flip a light switch and the bulb turns on instantly. You were told electrons flow through the wire like water through a pipe. That's not right. The electrons in your house wiring drift at about 0.1 millimeters per second. A snail moves 800 times faster. If electricity were electron flow, it would take over 3 hours for a signal to travel 1 meter of wire. So what is traveling at near light speed when you flip that switch? The answer rewrites everything you were taught about circuits. And it starts with a man who never went to university, taught himself mathematics from textbooks he could barely afford, and figured out something about electricity that most physics students still don't learn properly today. His name was Oliver Heaviside. But I will tell you about him in a moment. First, let me tell you what you were taught. You probably had a teacher at some point who drew a circuit on a blackboard. A battery on one side, a light bulb on the other, wires connecting them. And the teacher said something like this: electrons flow out of the negative terminal of the battery, travel through the wire, pass through the light bulb where they give up their energy, and return to the positive terminal. Like water flowing through a pipe. The battery is the pump. The wire is the pipe. The bulb is the wheel that the water turns. And you nodded because it made sense. It is a beautiful, tidy picture. Electrons carry energy the way trucks carry cargo. They pick it up at the battery, drive it to the bulb, drop it off, and drive back for more. Now, this is one of those cases where the simple explanation is not just simplified. It is genuinely misleading. And the right explanation is much more interesting. Let me show you why that water pipe picture falls apart. Take a standard copper wire in your house. It is carrying about 15 amps of current, which is a perfectly ordinary amount for, say, a toaster or a space heater. Inside that copper wire, there are free electrons. Copper is a metal, so its outermost electrons are not bound to any particular atom. They are free to move around. The number of these free electrons is enormous. In a cubic meter of copper, there are roughly 8.5 times 10 to the 28th free electrons. That is 85 billion electrons in a space the size of a large suitcase. Now there is a simple equation for how fast those electrons actually drift when current flows. You take the current, divide by the number density of free electrons times the cross-sectional area of the wire times the charge of a single electron. Physicists write it as V equals I over NAQ. When you work that out for a typical household wire carrying 15 amps, you get something astonishing. The electrons drift at approximately 0.1 millimeters per second. Let me put that in perspective. At 0.1 millimeters per second, an electron would take about 4.5 hours to travel 1 meter. 1 meter. That is about the distance from your light switch to the ceiling. 4.5 hours. Yet when you flip the switch, the light turns on in nanoseconds. Billionths of a second. Think about that. The electrons are barely moving. They are shuffling in place, bumping into copper atoms billions of times per second, drifting so slowly you would need a microscope and extraordinary patience to watch them move. If the energy traveled with the electrons at their pace, you would flip your light switch at breakfast and the bulb would turn on around lunchtime. So something else is carrying the energy. Something that moves at nearly the speed of light. And it is not inside the wire at all. This is where the real story of electricity begins. And it is a story about fields, not particles. You see, when you flip a switch and close a circuit, what happens is not that electrons start marching from the battery to the bulb. What happens is that an electromagnetic field propagates outward from the switch, along the wire at somewhere between 50 and 99% the speed of light, depending on the materials involved. This wave, this disturbance in the electromagnetic field, is what delivers energy to the bulb. The energy is not inside the wire. The energy is in the space around the wire, in the electric field and the magnetic field that surround it. Let that settle for a moment. Every wire in your house, every power cable in your city, every transmission line spanning the countryside, none of them are pipes full of flowing energy. They are guides. The energy flows through the fields surrounding the wire, and the wire simply shapes where those fields go. Like railroad tracks guide a train, the wire guides the energy-carrying field. The train does not flow through the tracks. The tracks tell the train where to go. The wire tells the field where to go. The field carries the energy. And this understanding This complete overturning of the water pipe picture came from one of the most remarkable self-taught physicists who ever lived. Oliver Heaviside was born in 1850 in Camden Town, London. He was partially deaf from scarlet fever as a child. His family was poor. He left school at 16, got a job as a telegraph operator, and that was the end of his formal education. But Heaviside had a mind that could not stop working on problems. He would sit at his telegraph station during quiet hours and study. He taught himself calculus. He taught himself differential equations. He taught himself French and German so he could read scientific papers. And the problem that obsessed him, the problem that would define his entire life, was electricity. What was it really? How did it actually move? In 1873, James Clerk Maxwell published his treatise on electricity and magnetism. This was one of the most important physics books ever written. In it, Maxwell laid out 20 equations that completely describe how electric and magnetic fields behave. Maxwell's equations predicted that changes in electric and magnetic fields propagate through space at the speed of light. Maxwell realized this meant light itself was an electromagnetic wave. He had unified electricity, magnetism, and optics into a single framework. It was, and remains, one of the greatest achievements in the history of physics. But Maxwell's treatise was dense, mathematical, and extremely difficult to read. Most professional physicists struggled with it. Heaviside, working alone with no academic position, no colleagues, no degree, got hold of a copy and taught himself the mathematics needed to understand it. And then, and this is the remarkable part, he went further than Maxwell had. It was Heaviside who compressed Maxwell's original 20 equations into the 4 elegant vector equations we know today. Those 4 equations you see on t-shirts and coffee mugs and tattoos on physicists' arms. That formulation is Heaviside's, not Maxwell's. Maxwell wrote the physics. Heaviside made it beautiful. But Heaviside did more than simplify the notation. He realized something about those equations that most people were missing. Something profound. The wires in an electrical circuit do not transport energy. They guide electromagnetic waves. The energy travels through the space around the wires, not through the metal itself. He was explicit about this. He wrote about it clearly and repeatedly. And most of the physics establishment ignored him because he was an outsider with no credentials and a sharp, sometimes abrasive writing style. He feuded with the Royal Society. He sent papers to journals that went unpublished. He spent years in relative obscurity, living in poverty, working alone in boarding houses and rented rooms, producing mathematics that would take decades for the rest of the world to catch up to. Around the same time, in 1884, a physicist named John Henry Poynting at the University of Birmingham independently worked out the mathematics of how electromagnetic energy flows through space. Poynting derived what we now call the Poynting vector. It is the cross product of the electric field and the magnetic field, E cross B, and it tells you the direction and magnitude of energy flow in an electromagnetic field. Here is the thing that surprises almost everyone who encounters this for the first time. For a current-carrying wire, the Poynting vector points radially inward, toward the wire, not along it, not through it, toward it from outside. Energy flows from outside the wire into the wire, not through the wire. The wire is not a pipe, it is a guide. The electromagnetic field carries the energy, and the wire shapes where that field goes. So every time you plug in a lamp, the energy that lights the bulb does not travel through the copper. It travels through the electromagnetic field in the space between the wires and around the wires, guided by the copper, and enters the bulb from outside. The copper is not the road. The copper is the guardrail. I find this genuinely beautiful. The forces between charged particles, the fields they create, the way those fields reach across empty space. That is the story of electricity. Not the particles themselves, not the electrons, the fields. Now there is something I have not told you yet, something that makes this even stranger. And it has to do with the current running through the wires in your house right now. In North America, the current in your walls alternates direction 60 times per second. In Europe, 50 times per second. This is alternating current, AC. And it means the electrons in your wiring are not flowing in one direction. They are oscillating back and forth, sloshing a tiny distance one way, then a tiny distance the other way, 60 times every second. How far do they actually travel in each half cycle? Less than a millimeter. Not even a full millimeter. The electrons do not go anywhere. They are essentially vibrating in place. Yet energy flows continuously and reliably to every appliance in your house. Your refrigerator runs, your lights stay on, your computer operates. All of this energy delivery is happening while the electrons themselves are doing nothing more than wiggling back and forth by a fraction of a millimeter. If the electrons were the carriers of energy, alternating current would make no sense at all. The electrons never arrive anywhere. They never complete a journey. They never deliver anything. The water pipe analogy would predict that AC current should be completely useless. Water sloshing back and forth in a pipe does not turn a water wheel. But the electromagnetic field does not need the electrons to travel anywhere. The field propagates at nearly the speed of light regardless of what the electrons are doing. The electrons are just there to support the field, to keep it organized, to maintain the boundary conditions that allow the energy to flow where it needs to go. They are the scaffolding. The building is the field. And there is a beautiful phenomenon that makes this visceral. It is called the skin effect. At high frequencies, current does not flow uniformly through the cross-section of a wire. Instead, it concentrates near the surface. The higher the frequency, the thinner the layer of current. At the 60 Hz of your household wiring, the skin depth in copper is about 8.5 millimeters, enough that current flows through the entire cross-section of most household wires. But at radio frequencies, say 1 megahertz, the skin depth shrinks to about 65 micrometers. That is less than the thickness of a human hair. The current exists only in the outermost skin of the wire. The interior of the conductor carries essentially zero current. Think about what that means. At high frequencies, you could make the wire hollow, completely hollow, just a thin metal tube, and it would work just as well. Because the energy was never inside the wire to begin with. The interior of the conductor was never participating in energy transfer. Even the electrons at the surface are just there to maintain the boundary conditions for the electromagnetic field. This is not some theoretical prediction. This is how we actually build things. Waveguides. The rectangular metal tubes used to carry microwave signals are literally hollow metal pipes with nothing inside them. No wire. No conductor running through the middle. Just empty space enclosed by metal walls. An electromagnetic energy propagates through that empty space, guided by the walls, exactly the way Heaviside said it would. The wire is a waveguide. That is the correct way to think about it. Not a pipe for electrons, a guide for electromagnetic fields. Now, I want to tell you about a thought experiment that illustrates this with brutal clarity, because it strips away every last hiding place for the water pipe intuition. Imagine a battery and a light bulb connected by two parallel wires, each 300,000 kilometers long. That is roughly the distance light travels in 1 second. The wires go out 300,000 kilometers into space and come back. Now, if energy traveled through the wires, if the electrons carried the energy like water through a pipe, the light bulb would not turn on for at least 2 seconds. 1 second for the signal to travel out through one wire, and 1 second for it to travel back through the other. At minimum. And if the electrons themselves had to carry the energy at their drift velocity, you would be waiting for millions of years. But that is not what happens. The electromagnetic field does not have to travel through the wires. It propagates through the space between the wires. The battery creates fields, and those fields begin propagating outward at the speed of light from the moment the switch closes. The space between the two long wires, right near the battery, is where the field first establishes itself. And if the bulb is sitting near the battery, separated by just a short gap, the field reaches the bulb almost immediately. Not in 2 seconds. Not in millions of years. In nanoseconds. The bulb begins to glow before the electromagnetic signal has traveled even 1% of the way along those enormous wires. The wires could stretch to the moon and back, and the bulb would still light up almost instantly because the energy never needed to travel through the wires. It only needed the fields between them. This thought experiment sparked enormous debate when it was presented to millions of people online. Over 20 million people watched and argued about it. And the arguments were fierce precisely because the answer is so deeply counterintuitive. We are trained to think of wires as pipes. We are trained to think of electrons as the important thing. But the physics is clear. The energy is in the fields, not in the metal. Now, you might wonder, how did we get the wrong picture so firmly lodged in our heads? How did humanity spend centuries thinking about electricity as a flowing fluid? The answer goes back to Benjamin Franklin. In the 1750s, Franklin proposed the model of electricity as a fluid, a single fluid that flowed from one object to another. He imagined that objects with an excess of this fluid were positively charged, and objects with a deficit were negatively charged. And he defined conventional current as flowing from positive to negative, from the excess toward the deficit. It was a reasonable guess for the 1750s. It was also wrong about the direction. But the real damage came later. In 1897, at the Cavendish Laboratory in Cambridge, a physicist named J.J. Thomson did something extraordinary. Using cathode ray tubes, glass tubes with the air pumped out, and electrical terminals sealed inside, he showed that the rays streaming from the negative terminal were not waves, as many believed, but streams of tiny particles. He measured their charge-to-mass ratio and found they were far lighter than any atom. He had discovered the electron, the actual carrier of electric current. Thomson showed that these particles were negatively charged, and they flowed from negative to positive. The opposite direction from what Franklin had assumed a century and a half earlier. But by 1897, the convention was deeply embedded in physics and engineering. The equations all work perfectly well with conventional current because the mathematics does not care which direction you call positive. So nobody bothered to change it. To this day, in every circuit diagram you will ever see, current is drawn flowing from positive to negative, while the actual electrons are moving from negative to positive. This historical accident still confuses students. It is a linguistic trap, not a physics error. But it combined with Thomson's discovery in an unfortunate way. Thomson proved that electricity involved discrete charged particles, electrons, and this led naturally to the mental model of electrons flowing through wires like marbles through a tube. It is vivid, it is concrete, and it is almost completely misleading about where the energy actually is. You see, Thomson's discovery was enormously important. He found the electron. That matters. But the discovery got tangled up with the wrong picture. People heard particles are flowing and thought the particles carry the energy. They do not. The particles are sources of fields. The fields carry the energy. The person who got it right, who described it correctly with mathematics half a century before Thomson found the electron, was Maxwell. His 4 equations, first published in 1865 and elaborated in his 1873 treatise, describe everything about how electric and magnetic fields behave. They predict that changes in these fields propagate through space at the speed of light. They predict electromagnetic waves. They predict that energy is stored in the fields themselves. And here is something I find genuinely beautiful about Maxwell's equations. They do not talk about electrons. Not really. They talk about fields. The electric field, the magnetic field, how they change in space, how they change in time, how a changing electric field creates a magnetic field, and a changing magnetic field creates an electric field. And these two fields bootstrap each other across the universe at 300,000 kilometers per second. The fields are the fundamental reality. The charges are sources of fields, but the energy lives in the fields themselves. There is an equation for the energy density stored in an electromagnetic field. 1/2 epsilon naught times the electric field squared plus 1/2 over mu naught times the magnetic field squared. The energy is literally stored in the space around the wire, in the fields that permeate that space. not in the electrons, not in the copper, in the seemingly empty space surrounding the circuit. Think about that. The space around the wire in your wall, the air, the insulation, the gap between the live wire and the neutral wire. That space is not empty. It is filled with energy. The electric and magnetic fields threading through that space contain the energy that powers your home. The copper is just there to shape those fields, to tell them where to go. And the mathematics confirms it in every engineering detail. Transmission line theory, the engineering discipline that designs everything from power cables to the cables carrying data to your house, is built entirely on this understanding. The characteristic impedance of a transmission line, the quantity that determines how signals propagate, is the square root of the inductance per unit length divided by the capacitance per unit length. And what determines those quantities? The diameter of the conductors, the distance between them, and the material filling the gap between them. Not the metal, the space, because that is where the energy travels. You could swap the copper for silver, or aluminum, or any other conductor, and the characteristic impedance would barely change. But change the spacing between the wires, or change the insulating material between them, and the impedance changes dramatically. The engineers who design these systems know, even if they do not always say it explicitly, that they are designing the space around the conductors, not the conductors themselves. Now let me bring this back to where we started. You standing in a room, your finger on a light switch. You flip the switch. In that instant, you are not starting a flow of electrons from the power plant to your ceiling fixture. The electrons in the wire barely move. What you are doing is closing a circuit that allows electromagnetic fields that have been waiting, coiled in the space around every wire in your house, to rearrange themselves. That rearrangement propagates outward from the switch at nearly the speed of light. Within nanoseconds, the fields around the wire leading to your light bulb reconfigure, and energy begins flowing from outside the wire into the filament. The filament heats. The bulb glows. The electrons in the wire between the switch and the bulb drift at 0.1 millimeters per second. If you could paint one of them and watch it, it would take hours to travel the length of the wire. By then, you will have turned the light on and off 100 times, read a book, gone to bed, and woken up again. That electron will still be shuffling along, bumping into copper atoms, having accomplished essentially nothing in terms of energy delivery. The energy was never in the electron. The energy was in the field. And this is not some theoretical abstraction, some mathematical curiosity that only matters to physicists with chalkboards and tenure. This is the literal mechanism by which you are alive right now. The screen you might be watching this on receives electromagnetic waves through space. The signals in your nervous system are electromagnetic pulses propagating along nerve fibers guided by the myelin sheath, the same way electrical energy is guided by copper. The power grid that keeps your world running. Every generator, every transformer, every mile of transmission line, all of it is electromagnetic fields, propagating through space, guided by conductors, delivering energy at nearly the speed of light, while the electrons stand around and jiggle. Oliver Heaviside figured this out in the 1880s, working alone, with no degree, no laboratory, no colleagues. He saw through the water pipe metaphor to what was really happening, and he spent decades trying to explain it to people who were not ready to hear it. He lived his final years in Devonshire, in poverty, reportedly using granite blocks as furniture because he could not afford proper tables and chairs. The Royal Society had rejected his papers. His work on transmission line theory and vector calculus and operational methods in mathematics, work that would later become foundational to electrical engineering, to telecommunications, to the entire modern world of signal processing, was largely unrecognized during his lifetime. He wrote near the end of his career that the role of the wire is not to carry the current in the way a pipe carries water, but to guide the energy that flows through the surrounding space. The wire, he said, is merely a boundary condition, The real action is in the field. He was right. Maxwell's equations prove it. The Poynting vector proves it. Every transmission line ever built proves it. Every hollow waveguide carrying microwave signals proves it. Every fiber optic cable, every antenna, every radio tower proves it. A self-taught telegraph operator with no degree, sitting alone in rented rooms, saw the truth about electricity more clearly than most of the credentialed physicists of his age. Electricity is not what you think it is. It is not electrons marching through copper. It is electromagnetic fields racing through space, guided by metal boundaries, delivering energy from one place to another at nearly the speed of light. The electrons are just standing there jiggling. The field does all the work. You learned about the particles in school. Nobody told you about the fields. But the fields are what light your house. The fields are what carry your voice across the world. The fields are what make everything work. And every time you flip a switch, you are not pushing electrons through a pipe. You are releasing a wave of energy into the space around a wire, and that wave arrives at the speed of light. The electrons never even noticed.